As we seek to wrap up this example, we're looking for a pattern in the TNs. So we want to see how do we count the number of additional operations that it takes to get from, say, T0 to T1. So we're going to do this for T2 to see if we can establish a more concrete pattern. One of the things we should note is the final run, if you notice, seems to run one time. So for I equals, when I becomes the last index, that is when it becomes equal to n, we notice this runs one time. This runs two times for I equals 0. So for the first index it runs twice, then it runs once. For T2, we're going to repeat this process. So for T2, this is going to become 2, and this is going to become 2. So from I equals 0 to I equals 2, we're going to start at I equals 0. J will start off at 0. The reason J will start off at 0 is because whatever the current value of I is, that's what the starting index is going to be. That's going to require 2 flops. I equals 0, J equals 1 will require 2 flops. I equals 0, J equals 2 is our final index. That'll require 2 flops as well. Now, I becomes 1, but remember J is going to start at whatever the current I is, and since I is 1, J will start at 1, and it'll do 2 flops. Then J will increment to 2, 2 more flops will take place. And now we need to increase I to become its final value, which is 2. J will start off at 2 because the value of J goes from I to n, and this will create another flop. So that is it. Now it runs out of J's, runs out of I's, so this is terminated. And you'll notice here there are 3 runs for I equals 0, 2 runs for I equals 1, and only 1 run for I equals 2. So there seems to be a pretty consistent pattern here. You can see that this is going to run a total of 6 times, this is going to run a total of 3 times, this is going to run a total of 1 time. But since this runs 6 times and performs 2 operations per run, this is going to be a total of 6 times 2, which is 12 total operations. If we did this for T3, we would find for T3, we end up with 22. And now what we want to do is we want to see if we can detect a pattern in this sequence. So our sequence goes, so Tn, or I should say n and Tn. So when n is 0, Tn is 2. When T1 is 1, or when n is 1, T1 is 6, and then 12, and then 22. And what we're looking for is how do we figure out the next Tn from the previous Tn. So the next Tn, well, that'll include all the runs from the previous value of n, but notice that there's a pattern in the sequence here. This increases by 4, this increases by 6, this increases by 10. And it would be helpful if I actually wrote down the right number. If we did this, we would get 20, not 22. And so this increases by 8. So now the goal is to see how many more units we'll have for the next value of n, for one value of n higher. And we see that from T0, that increases by 4, but from 1 to 2, we have an increase of 6. So it appears we're somehow increasing by multiples of 2. How many multiples of 2? Well, I can't just do plus 2n, because if n is 2, n becomes 2, 2 times 2 is 4, but from n equals 1 to n equals 2, I actually have an increase of 6. So let's try n plus 1. If I do n plus 1, the number of additional increased values is going to be, let's see, if n is 3, then 3 plus 1 is 4, 2 times 4 is 8. Perfect, that's where my plus 8 comes from. So, for example, we should see that T1 is going to be T naught plus 2 times 1 plus 1, which is T naught plus 4, which is exactly what I want. Then I should be able to check that T2 is all the operations from T1 plus 2 times, in this case this will be 3, which is T1 plus 6, and T2 is exactly T1 plus 6. So in general, I could say that the number of flops required for n iterations is the total number of flops required from n minus 1 iterations plus 2 times n plus 1. And now I can go ahead and solve this recurrence relation by using the method of iteration. And according to the method of iteration, we should now be able to construct the patterns, which we've already kind of done. We said T1 is T naught plus 2 times 2. T2 will equal T1 plus 2 times 3. But T1, we can now make a substitution here for T1. We could say T1 is T naught plus 2 times 2. That's my T1 right there. Plus 2 times 3. And T3 would be T2 plus 2 times 4. That's n plus 1 right there, 3 plus 1. And so now I'll make the substitution for T2. So that's going to be equal to T naught plus 2 times 2 plus 2 times 3. And then we're going to have plus 2 times 4. Now at this point, we know what T naught is, and we were starting to see the pattern here. T naught, recall, that is our value from the table up above, and T naught, the initial condition for this sequence, that value is 2. So the substitution I can make in here is to put in 2 for T naught, and that's really going to help me complete this. This is going to be 2, which by the way is also 2 times 1, plus my remaining terms, 2 times 2 plus 2 times 3 plus 2 times 4. And finally, I can try to establish a pattern here. I can see that T4 should be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. And in general, I should be able to say that Tn is equal to 2 times 1 plus 2 times 2 plus etc. But let's think about where this stops. This quantity here in the parenthesis, and this quantity here in the parenthesis, and this quantity here in the parenthesis, and this quantity here in the parenthesis is actually 1 unit bigger than n. So this will go up to 2 times quantity n plus 1. Now I see that this is an increasing arithmetic series. It's the sum of the first n plus 1 integers, non-negative, non-zero integers. So this, if I factor out a 2, this is 1 plus 2 plus ... plus all the way up to n plus 1, all of those individual positive whole numbers. And what I know is that if I want to add up 1 plus 2 all the way up to some n value, or whatever that last value is, that's going to be n times n plus 1 over 2. So we should see that whatever this is, that's going to be this, and that's going to be this. So if I want to sum to n plus 1, my final answer, finally, is going to be 2 times, well, this is going to be, my final value is n plus 1, so this is going to be n plus 1 times quantity n plus 1 plus 1 all over 2. So nicely here, these 2's cancel out. In the parentheses, I get n plus 1 times n plus 2. And if I distribute that, I'll have n squared plus 3n plus 2. And that's my final answer. So my time complexity function, t of n, is n squared plus 3n plus 2. And that's my final time complexity function. So sometimes when counting can be difficult, you can use this notion of applying recurrence relations to try to approximate for different values of n, starting at your initial, your smallest value of n, just counting the number of operations for a few values of n and then trying to look for a pattern in how the tn's increase. We write a nice recurrence relation, which is usually a fairly simple function for most of these. And then I can solve the recurrence relation using the method of iteration, and I get my final time complexity function. Now I should just be able to check that t0, if I put in 0 for n, I'll get 0 squared plus 0 plus 2, which is 2, and that matches with what we wrote in the table. Let's just check a few iterations ahead. Let's do t3. That's going to be 9 plus 9 is 18 plus 2 is 20. And that once again matches what we have in the table. So this is an application of it. Oftentimes we use recurrence relations because these can become pretty sophisticated to try to write, especially if you have loops or you have different things that do not start and terminate at constant values. Typically, when you have a nested loop that involves an index from another iterable, another for loop, you want to go about doing it this way. Again, these can become much more complex, and there exist a lot of simpler formulas for it, but to delve into the basics of it, this is totally adequate.